Hi, this is Maria, and we're going to talk about factors affecting rates of reaction. We're going to talk about two different things. We're going to talk about reviewing those ways that you discussed in class, and a few more that maybe you didn't quite get to in class, on how to actually speed up reactions. And then we're just going to talk about a few graphs of chemical reactions, and honestly just thinking about how graphs in general should be formatted. All right, so this is just a great picture that I loved, and I just wanted to kind of review some aspects of collision theory. Remember, there are two things that are really, really important for having a successful collision. Successful collision is going to have the correct orientation, and it's going to have the correct amount of energy present in order to be able to do a successful collision. And remember, an effective collision, as it shows here, is really going to then lead to the correct amount of products. So that's just something to keep in mind when we're thinking about all of these different ways to speed up reactions. All right, so let's start with the first one, concentration. So the lower the concentration, the fewer the collisions you have. Higher concentration, more collisions. That's about all you need to know and think about. More stuff makes sense. There's going to be more things that are going to bump into each other, and the more things you have bumping into each other, the more successful collisions that you can actually have. An important note that you didn't discuss during class is about reactants that are gases. So you might often, especially if you're going and doing any research outside of these videos, you might see something about pressure, that's also something that can speed up a reaction. That's true but that's only true if we're talking about if one of the reactants is also a gas. If one of the reactants is a gas, the concentration actually then is impacted by increasing the pressure. But again, that only works if one of the reactants is a gas. All right, next one, temperature. So remember that in a colder temperature, that means your molecules are moving slower. So it's kind of shown in this little particle level diagram here. And then at a higher temperature, molecules are moving faster. And they chose to show that by showing kind of more wiggle lines behind the different molecules. Remember that the faster that those molecules are moving, the more collisions that will occur. The more collisions that occur, more successful collisions that occur, more successful collisions that occur, and the faster the reaction goes. So just keep that in mind. For this one, it's a good visualization to take a look at a PhET experiment. Now again, because this is a JavaScript one, I'm going to just kind of show you guys for this. But if I'm looking at my A and my BC, and then A, B, and C are my products, you can kind of see at this lower temperature that, yeah, there are collisions. They're happening, but there's not a lot of collisions that are happening, and they're also not happening at the right energy. So let me go ahead and raise the temperature real quick. Okay. So as I'm raising the temperature, you can see several things happening. Well, one, the molecules have a lot more energy. They're bouncing around a lot more. And then you can also see that because they're bouncing around a lot more, there's a lot more collisions happening. And since that's happening now, you can start seeing that, oh, some of my products are actually starting to form. I have some C, I have some AB, all that sort of stuff. All right. So, go back to this. Just keep that in mind for when we're talking about temperature. Just that sort of visualization in your head when you're thinking about, oh, okay, slower with colder temperatures, faster movement with higher temperatures. All right, surface area. Remember, more surface area, more collisions possible. You can increase surface area in a few different ways. One of the ones that you saw in class was the aerosolizing of flour. And of course, one easy way to do it, stirring. So if you're looking at this particular example where the magnesium atoms are all black and I have a very slow surface area, you can see that if you were to stir up this mixture, you'd have a much higher surface area because you have the magnesium atoms distributed more evenly throughout the mixture. And so therefore you have more of a chance for collisions with both the water and the acid particles in this particular case to potentially have a reaction. Another thing that can definitely increase surface area is the particle size itself. So the smaller the particle size, the larger the surface area. So if I'm looking at this large marble chip here, that's not going to have as many opportunities for successful collision because it doesn't have as much surface area. But as if I compare over here, where there's a much smaller marble chip, there's more opportunities for collision. And so therefore, if there's more opportunities for collision, remember there's more opportunities for successful collisions, and therefore more opportunities for a reaction to occur. All right. Now, for an addition of a catalyst, just a few things to touch on. So when we talked about this in class, one of the big things that we talked about was using the potassium iodide as a catalyst in the decomposition of hydrogen peroxide. And your teacher showed you something along this line where, oh, okay, there's the activation energy, but it's lowered once you add a catalyst. Catalysts act in a few different ways, so the only thing that we really want you to be aware of is the things that I have listed on the side. It's not consumed in the reaction, and it's not listed in the reactants or the products. Usually if we're talking about a catalyst, it'd be kind of like what's down here, where if I'm looking down here, if I'm looking down here in this equation, you can see that over the arrow that it has HF, and then under the arrow it actually has 300 Kelvin. That's actually telling you a little bit about the reaction conditions of this particular one. What it's really saying is that the HF was used as a catalyst, and 300 Kelvin is actually just another way of measuring temperature. So just keep that in mind. Sometimes you might see some sort of information about what sort of reaction conditions you have. Sometimes you don't need that. Sometimes it's not included, but just keep that in mind as well. As I said, the big thing to remember about catalysts is really that you're lowering the activation energy of the reaction. And you could also have this drawn in a different way. You could have also created a different pathway where maybe there's different multiple transition states, but the activation energy is lowered. There's a bunch of different things that could happen, but just keep that in mind. It's not consumed in the reaction, and it lowers the activation energy. Other thing, just a quick reminder, remember activated complex is the same thing as transition state. It's just saying it is another way. All right, so last thing I want to chat about is how we talk about reactions using graphs. So I've graphed here a very, very general sort of situation that could occur. So I have the effective condition on the number of productive collisions over time. And you can see in condition 1 that you see almost immediately a very quick jump into a correct number of productive collisions. Remember that at the number of productive collisions, well, that would correspond pretty well to essentially how much product you're starting to make. So that's what we're looking at here. I also wanted to point this out. So you're like, what do you mean of condition? I could really use this for pretty much any of the things that I discussed in this video. The effect of greater surface area on the number of productive collisions over time. The effect of increased temperature on the number of productive collisions over time. It's just something to kind of keep in mind. And then just as kind of a preview for what we're going to be asking you to do this semester, and something that's helpful to just keep in mind, when we're talking about graphs, they should definitely include pretty much everything that I have here. You need a descriptive title, usually one that's commenting on both what's on the x-axis and what's on the y-axis, as well as whatever condition you're actually testing. Whatever, I should be able to figure out from your title of your graph what is exactly contained in the graph itself. The axes must be labeled with units. And so here I did time was in seconds, and then here it's the number of productive collisions. So it's essentially already written into the axis label itself. Sometimes you might need a legend, so something along the lines here where I'm looking at condition 1 versus condition 2. Maybe if I was doing different temperatures, something like 10 degrees Celsius could be one of these, and 20 degrees Celsius could be another one. Something like that when going through. You don't necessarily always need that, but just keep that in mind. If it's a scatter plot graph, which is going to be what you'll do for chemistry, the individual points should be connected with straight lines, not with curved. If you end up putting a little bit of a curved line on it, there's that function in Excel that actually starts implying data that you don't actually have. So please keep that in mind. Connect the points because it is helpful for visualization. don't connect it with those curved lines. Not a good idea. And it should be large enough to be really easy to read. I should be able to see it, be able to quickly read it, and have it easy to understand just visually looking at it. All right, so just things to keep in mind as we move forward in the semester as well. All right, I want to come back to the key idea that you should really understand about reactions and different conditions and ways of speeding things up. So the key idea is really just increasing the number of collisions is going to increase the number of productive collisions just because you've increased the number of collisions, and therefore you're increasing the reaction rate. You just need to increase the number of collisions. The more collisions you got, the more productive collisions that you'll have. And the more productive collisions that you'll have, then the faster your reaction rate. All right, so here's our question. Again, reminder, you need to attempt this for full credit. So you've got two reactants mixed together. You have a solid, and we'll call that solid A, and then a solution, and we'll call that solution BC. The products of these two reactants are a solution of AC and of a gas B. The container that this is being mixed in gets very warm when the reactants are mixed. So go ahead, write a chemical equation that describes the above scenario. Don't overcomplicate it. Just think about it when you're going through. Definitely write down, is this exothermic or endothermic? And then this reaction becomes more vigorous once more BC is actually added. So explain using collision theory why. And I would definitely recommend particle level diagram to actually help your explanation. All right, well, that's it for this video. Go ahead, take an attempt at this question, and you'll discuss it in the next class. Have a pleasant day.